Welcome to Brain Vision.
In this problem we have a beam that is simply supported on its two ends here, and then there is some additions to the beam, and then some cables connected, and there's an 80 Newton load on it, and with these two here. So what the question that we want to answer is that these distances here can be varied, and we'd like to minimize the maximum absolute bending moment in the beam. Figure out how long these should be to do that. So what we can do is we can figure out that, well, because of symmetry, both of these, the y components, have to be 40 newtons each, and their x components have to be equal and opposite, and because of geometry, the tangent of theta is 2, and so we wind up with, this would be 80 newtons. So we have 80 newtons acting this way, and obviously those are acting to bend the beam. And so we have, if we draw a free-body diagram of our beam now, with the forces and bending moments on it, this one will be, this one will be positive, this one will wind up being negative. So we have these this whole situation here, and we can figure out, again, we can do a force and moment balance on this, figure out what FAY and FBY are. I'm not going to go through all of that in detail, but what we find out is if we draw, if we make our cuts, so let's say we make our cuts here, 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 so we have shear forces and bending moment in each of these. Well, we see that we'll have for shear forces, their shear forces are constant in each of these regions, and what we have is a shear force in this region that's constant, so our bending moment is going to start at 0, and it's going to decrease less than 0, and then at this point shear force will jump, but the bending moment will also jump by whatever the magnitude of this. And then at this point, again, the shear force is constant in this area, and in fact, it turns out it's 0 in that area. And then it's positive in this area, and so we'll have a positive slope in the bending moment. So if you play around with this a little bit, what you'll find is that the peak moments, negative moment occurs at either one of these points here. So that's when x equals a. So when at m, the value of m at x equals a turns out to be minus 40a. And then the other peak occurs, basically is constant in this region here. So there's basically a jump, and it jumps from its minimum to its maximum. And so, and then I just basically picked the middle point. So the middle point here is a plus 1/10, and everything's in meters here. And so we get this expression for the moment at the midpoint. So at this point, and so what we want to do is we want to make this equal to this, the maximum value of this equal to this. And if we do that, we set these two things to get equal, and we find out that a is 0. It's 40 millimeters, and that's this case I showed right here, where you can see that m is 1.6 newton meters here, and minus 1.6 newton meters here, and 1.6 newton meters here. So that's when our magnitude of the maximum magnitude of the bending moment is the smallest. Now I showed some other little schematics here of when we have 20 millimeters, you can see that the region it's lower here, but it's greater here. And then for 60 millimeters, it's greater here than and it's lower here. So these are kind of two cases where we've gone away from the optimum of 40 millimeters, and you can see how kind of as A gets bigger, this thing decreases, but so does this. And A gets smaller, this thing decreases. Well, as A gets smaller, as A gets bigger, this thing increases in magnitude, this thing decreases in magnitude. When A gets smaller, this thing decreases in magnitude, and this thing increases in magnitude. And the optimal value is 40 millimeters.